All right, welcome everybody. Looking at 4.5 today, a topic called linearization and something called Newton's method. And at the end today, looking at something called differentials, which is going to look a lot like something we've already done before. Now, the linearization thing is actually really, really cool. You might not even grasp how cool it is, but let's see what it's going to look like here. All right, so linearization is kind of an interesting topic, and let's just get some definitions and stuff out of the way first. If f is a differentiable function at x equals a, then the equation of the tangent line, something we already know how to do, is L of x. So that big L is the idea that we're taking a linearization, is f of a plus the derivative at a times x minus a. And you might look at that formula and go, that's kind of weird looking, but it almost seems familiar. And it kind of should, because right in here, f prime at a is slope. A is a point, so this is x minus a, and this is f of a. So this a is your x value, this is your y value. That just means this is the point slope formula. And some of you are like, oh, right, yeah, okay, I knew that. So this is point slope formula. Now, what we're kind of getting at here is trying to estimate values at specific points. And what linearization is telling us is basically if we zoomed in at a specific point on a graph, and we just kept zooming in and zooming in and zooming in, eventually, even if we were looking at a quadratic function, if we zoomed in at a point, eventually your calculator, it would look like a straight line. And that's what linearization means. It's basically as close as we get to that a value, the straighter that line is going to approximate or approach. All right, and that's kind of our idea of tangent line anyways, because we would think that that's kind of what it looks like at that point. It was a really straight line, right, really close to that a value. Okay, so this particular statement here, this defines the linearization of f at a. That's the L of x there. And the point x equals a is the center of the approximation. And what we're going to be saying basically is f of some value, we'll call it x, is approximately the same thing as L at that value. And if we want to use some other value here, we can say, okay, f prime, or sorry, not f prime, not today, f at B is approximately the same thing as L at B, because what we're looking at is something really close to this A value. All right, so let's kind of keep going here. And like I said, what we're going to be doing is approximating. And this is what's kind of cool about this, is because you can now approximate a radical without using a calculator. So if I told you, hey, what's the square root of 5? And most of you would pull out a calculator and you just go for that, right? Or what's the square root of 123? And that's actually a problem we're going to be doing here in a moment. 123 is not a nice number, but there is a nice number close to it. All right, so what we're going to do in this particular case, we're going to approximate the square root of 1.02 using the linearization of the function square root of 1 plus x. You'll notice that the square root of 1 is a nice number, and we're just adding something to that 1. And notice this approximation, we're adding 0.02. I'm going to get to that in a second. So kind of something that we're going to need to do is find the derivative. We actually need to find that line, that linearization. We need to find L of x. So I need to figure out f of 0 kind of first, because I need to know what point we're going through. Well, f of 0 is the square root of 1, which is 1. So we're going through the point 0, 1. That's super important for us. And then I need to figure out what is the derivative of x. So the derivative of x is the derivative of the inside, which is just 1, so that's nice, times the derivative of the outside. And I hope you all remember that this is the derivative of a square root function. And then we need to find the derivative at 0. So I know you could have done this all at once, but I'm just going to kind of do it this way. I can find the derivative at 0, so it's 1 over 2 times radical 1, which is 1/2. And now I'm going to find the linearization model, the equation here. L of x is going to be f of a. Well, f of a is 1 plus my derivative at a, which is 1/2, times x minus a. Well, a was 0. So I get a very simple linearization function, which is 1 plus half x, or x over 2. Okay, that's just simplifying this statement there. Well, that's all well and good, but then it's like, what do we do with that? Well, in this particular case, we're going to approximate the square root of 1.02 by looking at the original function and looking at 1.02. This is where I mentioned we're looking at basically 1.02 is f of 0.02. So we're looking to approximate f of 0.02. Well, that is what I can do down here. I just said a minute ago that f of a value is approximately equal to the linearization at that value, which is equal to 1 plus 0.02 over 2. And notice I have not even touched a calculator yet, and 1 plus 0.02 over 2 is actually 1.01. Now some of you are like, well, yeah, that's easy, but what does that mean? Well, go plug the square root of 1.02 on your calculator. If you plug this into your calculator, the square root, I'm doing this right now actually, 1.02 is, on your calculator, 1.00995, and if you just keep going to what's left on the calculator, 0.494. Notice how close this approximation was. That's insane. At least I think it is, but I'm weird, but right? So notice how close this was. Just by using a simple derivative, we could approximate this square root. We're going to do this a couple more times coming up, so don't get too overcomplicated here. All right, so or too confused here. So this is so cool. All right, so let's move forward from this particular problem. Let's do the same kind of thing, only this time with a cosine function. All right, so remember one of the first things that I did was I found what was f of pi halves. All right, so f of pi halves is the cosine of pi halves, and I hope you all just instantly told me that this was 0. That should be on the tip of your tongue. You should know that already. All right, then I need to find the derivative of f. And the derivative of f, again, another one of those, oh, where'd this SO come from? One of those you should just have memorized by now. And notice this process is exactly the same, just a different function. Now I need to find f prime of pi halves, which is the negative sine of pi halves, which is, sine of pi halves is normally 1, negative of that makes -1. And then I get to do this pretty simple L of x. L of x is f of a, which was 0, minus, in this case, because it's a -1, it would normally be plus a -1 here, but I'm going to just write it as a -1, times x minus pi halves. If I simplified this down, this is going to get me a pi halves minus x. Now don't forget the purpose of this linearization function. I can now say, okay, f of 1.75 is approximately equal to L of 1.75, which is equal to pi halves minus 1.75. Now in this particular case, you have to pull out a calculator just to get what that approximate value is. And if you did that, pi halves minus 1.75, I get negative 0.179204. Let's just go out that far for now. And then what I can do is I can just figure out, hey, what actually was the cosine? Let's see how close this was. I didn't mention this, but make sure your calculator is in radian mode or it's not going to work. And notice that if you're in radian mode, you get negative 0.178246. Again, that is so awesome. I mean, you're only a thousandths off. Okay. Now, something I didn't really mention here is you have to be very, very close to your center of linearization. Okay, that a value. Pi over 2 is what? Pi divided by 2 is 1.57. So 1.75 is kind of close. The farther you get away from this a value, the less this is approximating. Because you think about a curvature of a line, your straight line's not really going to follow that curve very long. It's going to have to be very, very close to your a value in order for this to actually work correctly. Okay. So all right, one more like this. Actually, I got two more. Sorry, I forgot what questions are coming up next here. I want to use linearizations to approximate the square root of 123. So what we need to think about is the fact that we're kind of taking the square root. So I'm going to look at the function square root of x. And I could go ahead right away and figure out what the derivative is, because this one's an easy derivative. 1 over 2 radical x. But then the problem is where am I centralizing? Where am I focusing in on? What a value should I use? Well, I want to use a values that I don't need a calculator for. So I want to use something close to 123 that is a good number, meaning a square root of square number. Well, it just so happens that I chose a very good number here because 123 is really close to 121. So I'm going to look at f of 121 being 11. And then I can do the same thing. F prime of 121 is going to be 1 over 2 times 11, so 1 over 22. Well, that means I have everything I need now. I can take the linearization function and I can say this is 11 plus my slope at a, so 1 over 22, times x minus 121. And then if I want to figure out the question being asked now, I can say, okay, f of 123 is approximately equal to the linearization of 123, which is pretty simply 11 plus 1 over 22 times 123 minus 121. This is now just plugging in x values, by the way, which is 11. If you did this, this is 2 in the parentheses. So 2 over 22 is 1 over 11. You may or may not know that 1 over 11 is actually a pretty cool decimal. It's 11.090909. And then we always like to just confirm that we're pretty close to the original, or to the actual. So if I said, what is f of 123 originally, it would be the square root of 123. And that on your calculator comes out to 11.09. Look at that. We're already like super, super close. And we're even super, super close to the thousandths. And then we start to break down a little bit because you can only be so good. But there we get our linearization, our approximation of the square root of 123. I have another example here. I hope you might be able to pause the video and try the example for yourself before I get started. This particular one is the cube root of 123. So if you want to pause, do so now. I'm going to go ahead and start this. I'm going to look at the function f of x equals the cube root of x. And I'm going to do the same thing as before. F prime of x is 1 over 3 times the cube root of x squared. Again, not a super challenging derivative. But then I need to figure out what a value am I going to go to. Well, since it's a cube root, it just so happens that 123 is really close to 125. And 125 is a perfect cube. It's a cube of 5. So I'm going to look at 5 being something really close. Oops, not 5. What am I doing? 125, silly. All right, 125. Come on, work like I want you to. Okay, looking at 125. Man, stupid thing. 125. Maybe it's just stupid user. All right, 1 over the square root, or 1 over 3 times the cube root of 125 squared. Man, troubles on this one problem here today. All right, cube root of 125 squared. Now, you can just take the cube root of 125, which is 5, and then you can square it, which is 25, and you can multiply by 3, which is 75. And then we just do our process again. L of x is 5 plus 1 over 75 times x minus 125. And then I want to know what's the approximation for f of 123, which is close to the linearization of 123, which is 5 plus 1 over 75 times 123 minus 125. And some of you are going, oh no, that's negative. It can't be negative. It doesn't matter because I'm taking a small negative away. And I get something that looks like, let's go 5 minus 2 divided by 75. And I get 4.973 with the 3's repeating. And I just like to double check what is the cube root of 123. And 123 to the 1/3 power is 4.973189833 according to your calculator. And notice we're super, super close. You could do this for almost any type of root you want. Okay, you can estimate anything you want as long as you're finding a number close to the approximation value you want. All right, so that's linearization approximations. Something else that came out of this is something called Newton's method. This, again, amazing, right? You don't even know what we're doing yet. Okay, so Newton's method is a way of finding solutions to the equation f of x equals 0. So basically a way of finding x-intercepts, a way of finding zeros of a function. So what you're going to do is you're first going to guess a solution. And this is where a graph comes in handy. So you probably graph it and you go, oh, it looks like the x value should be this. All right. And then you're going to use this simple yet complex looking formula. This just says I can take the next value is equal to the previous value minus f of that value divided by the derivative of that value. We're going to use our calculators pretty heavy here. Just know that in Newton's time, he had to do this by hand. And he could do this by hand. And it really actually, you'll see. You'll see. I can't even talk about it right now. All right. So we're going to use Newton's method to solve this cubic function. Now, you can still technically use a calculator to do this. But if anybody asks you to use Newton's method, you have to do it this particular way. All right, so a sketch of this graph might come in handy. And if you sketch this graph, it looks a little something like this, where this is -1 and this is 0, and you notice that it crosses the x-axis somewhere between -1 and 0. Now, I didn't draw this very good because technically the graph is really it's closer to the y-axis than it is to the -1. So my guess is x equals -0.2. Now, I could change this a little bit to show this, whatever. I'm going to say -0.2. The textbook uses -0.3 here. And if you want to compare mine to theirs, it's so interesting how fast this converges to the actual number. And what this does is it actually converges to the actual answer, the something that you could find here. So there's a couple things that I need to know. I need to know that f of x is x cubed plus 3x plus 1. If you know that little formula in the back, it had the function f and the derivative. So the derivative of x is 3x squared plus 3. This derivative is correct this time, unlike my last video. Okay. So then I want to figure out the next value. I know that x sub n is -0.2. That's my initial guess, which means my next value is going to be this value plus f at -0.2 divided by f prime at -0.2. And notice this formula is actually pretty simple. And when I do this, you can use your calculators here to help you do linearization. So what I did is I plugged the f function into my y1 and the f prime function into my y2. And then I can use the alpha f4 or alpha trace to evaluate. So what I would do here is I would just say -0.2 plus, and here I'm going to say y1 of -0.2 divided by y2 of -0.2. This is what I'm doing in my calculator. And give me a second to type this in. I get -0.32564 blah blah blah. The thing is this particular number is now an answer, an ANS on your calculator, which means my next approximation n plus 2 is going to be my answer, the previous number, plus f. Actually, because you've typed it into your y equals, you can go y1 of answer. I want to do the in there. Over y2 of answer. And once you get that, so go answer minus, or plus, I'm sorry, not minus. Oh, I'm sorry, it was supposed to be minus. I was writing plus in here. And it's one of those things where I'm doing the writing after I've done the work, okay? And I'm sure you guys will yell at me tomorrow, but it's okay. I go with the flow. All right, so answer minus. y1 at my answer divided by y2 at my answer. And in this particular case, I get -0.3221888, blah, blah, blah. Now, here's the super cool part. As soon as you've done this, x of n plus 3, all you have to do is hit enter. And if you hit enter again, it's just going to do the same calculation with the answer that it just gave you. And in this case, I get -0.322185. And if you just keep hitting enter a whole bunch of times, you'll notice that it keeps coming out to this particular number 0.3221853,546. And if you go into your calculator and you calculate the zero of your function on your graph, I bet you that's the number you come up with. I don't know about you, but that's pretty awesome. Okay, I'd honestly never heard of this until I went to that summer institute. This was just amazing to me. Okay, so there you go. You got one more little thing to kind of figure out here, and this is the idea of differentials. And this goes to the other guy, Leibniz, not Newton. And differentials are basically just the dx. The dx is the independent variable, and the dy is defined as, hey, look, there's the derivative. Okay, dy is the derivative of a function dx. So f prime dx. And what this is basically going to do is it's basically allowing us to use dx and dy as variables, even though they're not variables. It's really weird. It's one of those math calculus things where, if you remember, we were like saying, okay, the thing is zero, but not really zero. Okay, so this is kind of one of those areas. So we're going to find the differentials at dy and evaluate dy for the given values of x and dx. It's actually a pretty straightforward thing. The first thing you want to do is basically just find the derivative of both sides. So we're going to write dy. No y prime here. We're going to write it as dy. And this is basically 5x to the fourth dx plus 37 dx. And we can write it as 5x to the fourth plus 37 dx. And you probably could have written it like that beforehand, but I just like to do it this way. Notice that we kind of pretended like it was a variable because we just factored it out. It's kind of weird. But then we just got to figure out dy, and this is actually kind of cool here. We can figure out the derivative at these values by just plugging them in. And if you do 5 plus 37 times 0.01, you get 0.42, which is your answer. And that just means you found the derivative at y, given an x value and a change in x. Basically all it's asking. All right, so you can do this for any type of problem. This one's the same. Let's move to the last one, just kind of, because this one's a little bit different. I still want to take the derivative of both sides. So I'm going to take the derivative of the x plus y and the derivative of the xy. And what we're going to kind of look at is the left side here is actually just the sum and difference derivatives. So I can say it's dx plus dy. I'm taking the derivative of a sum, so I can take the derivative separately. This one is the derivative of a product, so I got to use product rule. So it's y dx, so it's y times the derivative of x, plus x dy. Well, now it's just the manipulation to get dy by itself. So I can say dy minus x dy is equal to y dx minus dx. That's a simple manipulation there. And here's where it gets kind of funny. I'm going to factor out a dy, get 1 minus x. And this is actually basically implicit differentiation, just looking a little bit different, okay, if you think about it that way. And this is equal to dx times y minus 1. And therefore dy is equal to y minus 1. Oops, let's get rid of those parentheses. Y minus 1 over 1 minus x all times dx. Now, in order to plug this stuff in here, the x and the dx, you needed to know what y was in the first place. So if you plugged x equals 2 into this equation, the original equation, you would actually find that y equals 2 as well. And that's pretty straightforward. So that means I can plug the stuff in now. I can say dy is equal to 2 minus 1 over 1 minus 2 times 0.05. Oops. And 2 minus 1 is 1. 1 minus 2 is negative 1. So that's negative 1 times 0.05, which is negative 0.05. All right, I hope you guys kind of felt this was pretty cool today, especially those approximation things and the linearization, the Newton's method. That's just awesome to me. All right, so what I'm going to do here is I'm going to break this assignment up. These two assignments here, the 4.4 and the 4.5, are kind of longer assignments. And I got another kind of part video that I got to upload this weekend for part B. So what I have for us is page 142. I'm just kind of breaking it up to number 28, and then the leftover ones for part B on Mondays. So the part A is what we are doing for Friday tomorrow. I hope you have the optimization problems done. I hope to also get a video up this weekend on all of the optimization problems, just working every single one of them. Even if it takes me an hour to do it, I will do all of them. All right, I might post it in a couple different videos. All right, so hang in there. This stuff gets fun if it hasn't been fun for you already. I'll see you guys tomorrow.